Hi, my name is Alexey Ilyin. I am an associate professor of physics at the Department of General Physics of MIPT. And today I will discuss solutions of problems that were offered to students at the MIPT-International Academic Olympiad that took place in December this year. There were 5 problems, and so we start from the first problem. The problem statement reads: a block of mass 3m lying on a smooth horizontal table is connected by a spring of stiffness k with a vertical wall. A pellet of mass m flying at speed v hits the block and gets stuck in it. The question is, find the period of oscillation of the block with the pellet stuck in it. In order to find the period of oscillations, we have to use the standard formula, which is shown here, for the period of oscillations of some mass which is on the spring of stiffness k. Here we must use the mass of the body that is oscillating on the spring, and the total mass is 3m, which is the mass of the block, plus small m, which is the mass of the pellet stuck inside the block. So the total mass is 4m, and the calculation is very simple, and here we get the answer for the period of oscillations. So the first question has its logical answer. The second question to this problem is, find the maximum deformation of the spring. This is somewhat more complicated problem. We have to use the law of momentum conservation. This law is applicable because the pellet interferes with the block for a very short period of time. And during this short period of interaction, there are no external forces acting on the system, the block plus the pellet. Because during this short period of time, the spring deformation is actually 0. The body has not started its motion, and so the spring is not deformed. Therefore, no external forces act on the system of the block plus pellet. So we can use the law of momentum conservation, which reads the initial momentum of the pellet equals the final momentum of the system, which consists of the block and the pellet stuck in it. And from this equation, we obtain the final velocity of the block, or the initial velocity of the block with the pellet. That is certainly the initial velocity, which is imparted to the block before the spring is deformed. Knowing this velocity allows one to apply a law of energy conservation. This law is applicable because there are no forces of dissipation, no friction. Therefore, mechanical energy is conserved in the process of oscillations. And so the initial kinetic energy of the block with the pellet stuck in it, which have the mass 4m, times velocity squared, the initial velocity, and all this kinetic energy will be transformed into potential energy of the spring when the deformation is maximum. The deformation is denoted by x maximum, which should be taken squared with the stiffness of the spring as coefficient. So the initial kinetic energy is equal to final energy of spring deformation. From this equation, we can obtain this x maximum, the value of maximum deformation of the spring, because we already know the initial velocity of the block. So solving this simple equation gives the solution to the second answer of this problem, which is indicated by this formula. So now we move to a second problem, which reads: a movable slide of height h and mass 7 m is at rest on a smooth horizontal surface. On top of the slide, there is a small block of mass 2 m. The block starts moving down the slide with 0 initial speed, gets down to the horizontal surface, and then runs along the track that has the form of a loop. So this problem deals with the slide, which is this object, which can move in any direction, to the right or to the left, without any friction. It can move along this horizontal surface, either to the right or to the left. And also a small block, which is on the top of the slide, starts moving without initial velocity. In this situation, the block will move to the right, and the slide naturally will move to the left along the surface without friction. So, as no external forces act on this system of two bodies, and as there are no forces of friction, no dissipative forces, we can use a law of conservation of energy and a law of conservation of momentum. So let u be the slide velocity and v be the block velocity when it is on the horizontal surface. So when the block slides down to this point, we designate its velocity as v. Using these notations, we can write the equation of energy conservation. The initial energy is the potential energy of the block, which has the mass 2m and the height h above the surface, and g is the acceleration of free fall. This initial potential energy is then transformed into the kinetic energy of the motion of the slide, which has the mass 7m and velocity u, and which moves to the left, and the kinetic energy of the block, which has mass 2m and velocity v, and it moves to the right. Also, the law of momentum conservation can be used in this problem because there are no external forces, only the internal forces of interaction between the block and the slide. And the law of momentum conservation reads: the mass of the slide times the velocity of the slide and equals the mass of the block times the velocity of the block. We understand that the slide moves to the left and the block moves to the right, and so what is written here is that the momentum of the slide equals the momentum of the block. Why so? Because the initial momentum of the system is 0, so the final total momentum is also 0. From this equation we can find the relationship between the two velocities v and u. So we have two equations, the equation of energy conservation and the equation of momentum conservation, and two unknown quantities, the velocity u and the velocity v of two moving bodies. So the two unknown quantities can be found from these two equations, and the answer is here, which can easily be found using simple algebraic transformations. So that is the velocity of the body which is moving at this point along the horizontal surface. This is the velocity of the body before it enters the loop. Now the second question to this problem reads: at what maximum radius of the loop the block will not break away from it in the upper point? So when the block enters the loop, we must understand that the loop has the form of a spiral, and the block moves here and then along the loop. And if the velocity of the block is not big enough, then the block may separate from the loop and fall down. This should not be the case according to the statement of this problem. The block, according to the problem, should slide along the loop, not separating from its surface. In order to find the answer to this question, we must introduce a new quantity, which is v prime, the block velocity at the upper point of the loop. From the energy conservation law, we obtain this equation. The energy conservation can be applied in this case because there are no forces of friction, no air drag. Certainly in such problems we never consider the air drag, and therefore the initial kinetic energy of the block will be transformed into the final mechanical energy of the block, which will consist of the potential energy and the kinetic energy of the block. The kinetic energy has simple form, which is the mass of the block 2m times velocity v prime squared of the block in the upper point of the loop. And the first term in this equation is the potential energy of the body of mass 2m, that is the block, and g is the acceleration of free fall, and 2r is the diameter of the loop, which is the maximum height of the block above the surface. So this equation allows one to obtain the velocity of the block in the upper point of the loop, v prime. That quantity can be found from this equation. Also, we must understand that when the block is in the upper point, the force acting on the block, that is the gravity pull, equal mass of the block times acceleration of free fall, equals the centripetal acceleration of the block, which can be expressed as the mass of the block 2m times velocity of the block v prime squared over the radius of the loop. This is because the centripetal acceleration of the moving body must coincide with the acceleration caused by the force of gravity. Only in this case the block will not separate from the loop. And from here we can find the v prime squared. Using equations 3, 4, and 5, using these equations 3, 4, and 5, we can find the final solution to the problem. That is, we can calculate the maximal radius of the loop at which the body will not break away from its surface. That is the final answer to the problem. Again, simple algebraic calculations allow one to obtain this answer based on the two equations, the equation of energy conservation and the condition that the centripetal acceleration of the block equals actually the acceleration of free fall. Such is the solution of the second problem. Now problem number 3. 1 mole of ideal monatomic gas expands along the isobar 1, 3. So on the picture, this expansion is shown by this line. During this process, the pressure of the gas remains constant. And then the gas cools down on isochor 2, 3. Along this process, the volume of the gas remains constant, and the temperature is decreased, and hence the pressure is decreased from point 2 to point 3. In transition from state 1 to state 3, the gas performs work A. The pressure ratio in states 2 and 3, the pressure ratio is given and is equal to alpha. And in states 1 and 3, the gas temperature is the same. So these 2 points, 1 and 3, belong to the same isotherm. The first question, find a change in the gas internal energy in process 1-2. The solution to this question is very simple. The internal energy of the gas can be expressed using temperature of the gas. And so the temperature difference, or the change in temperature, gives the change in internal energy. This coefficient is the number of degrees of freedom. As we have a monatomic gas, it has 3 degrees of freedom, which correspond to the movement along 3 perpendicular directions in a 3-dimensional space. So this is a standard formula which immediately gives the expression for the change in internal energy. Certainly, what is used in this formula is the gas law, the law of ideal gas. The pressure times volume occupied by the gas equals universal gas constant times temperature. This is for 1 mole. If we had more than 1 mole, then we should have multiplied this equation by the number of moles. But in this particular problem, the number of moles is 1. So, using this equation for an ideal gas, we immediately find the relationship between temperature and pressure and volume. And certainly, temperature in point 2, which is this point, is expressed using pressure in point 1, because this is the same pressure as in point 2, and then pressure in point 1 and volume in point 1 follow to find the temperature in point 1. So, using this expression, we obtain the work produced by gas in this process. All the work produced by gas is produced on the isobar, where the volume of gas changes, but the pressure remains constant. And in this case, the work produced by gas equals pressure times change of volume, which is used in this formula. So the answer to the first problem is found. This is 3a over 2. The second question is, find the gas temperature T1 in states 1 and 3. According to the statement of this problem, the temperature in state 1 and 3 is the same, so it's denoted by T1. All the notations used in this solution are indicated on the picture below. Pressure of the gas P1 corresponds to states 1 and 2, and pressure of the gas in point 3 is denoted as P2, which is not quite logical, but anyway, this notation is used in the solution. And also volumes. The volume in point 1 is denoted as V1, and the volume in points 2 and 3 is denoted by V2. So we express the work produced by gas using the gas equation, the equation of ideal gas, again the same formula. And then, using this equation, we form such a simple relationship between pressures and volumes and temperatures of this gas in two different points, and from this equation we find the relationship between temperatures and pressures. And this relationship is given in the problem, which is alpha. And now from these two equations, equation 1 and equation 2, we can easily find the expression, the relationship between work and temperature and the given coefficient alpha. And from this equation, we obtain the final answer, the temperature of the gas in point 1, which is the same as the temperature in point 3. Such is the solution of problem number 3. Now problem number 4. Inside a flat capacitor, there are two dielectric plates with electric permittivity epsilon 1 and epsilon 2 respectively. And the thickness of the second plate is twice as large as the thickness of the first plate, where d is the distance between two plates of the capacitor. The area of each plate of the capacitor is equal to S. First question, find the capacitance C of the capacitor. In order to solve this problem, we use the equivalent scheme, which in this case can be shown as follows. This is capacitor number 1 and capacitor number 2 connected in series. And the first capacitor is filled with dielectric medium, which has permittivity epsilon 1, and the second capacitor is filled with another medium with electric permittivity epsilon 2. So this equivalent scheme allows to calculate the capacitance of each capacitor C1, which is given by this formula, and the capacitance of the second capacitor, which is given by this formula. This is the standard expression for capacitance, which is proportional to the area S of the plates of capacitor and inversely proportional to the distance between the plates. And so the same is true for the second capacitor. The total capacitance of the two capacitors connected in series is calculated according to standard formula, and if we have expressions for each capacitance, then we can calculate C, the capacitance of the two capacitors connected in series. Simple calculations give us this result. The second question in this problem is, find the electric field strength inside the plate with dielectric permittivity epsilon 1 if voltage U is applied to the capacitor. So we suppose that we know electric field strength in the first capacitor, which is denoted as E1. If we know this electric field strength, then multiplied by the distance between the plates of the first capacitor, we obtain the voltage between the plates of the first capacitor. And if we add another voltage, which is on the second capacitor, then we obtain the voltage U applied to the capacitor, to the original capacitor between the two plates here. This is equation number 1. And then we use the connection between the electric field strength in the capacitor filled with some dielectric medium with permittivity epsilon 1 and the electric field strength in vacuum. That E0 would be the electric field strength in case there are no dielectric medium inside the capacitor. And if the capacitor is filled with some dielectric medium with permittivity epsilon 1, then the resulting field strength inside the dielectric medium will be less than the original field in vacuum. And the same is true for the second capacitor. From these two equations, we immediately obtain the relationship between the electric field strengths inside the two capacitors, E1 and E2. From the last two equations, equation 1 and equation 2, we immediately obtain the electric field strength inside the first capacitor, that is, here, in this region, in this area. Such is the solution to problem number 4. Now problem number 5. In the circuit shown in this figure, switch K is open. Then this switch is closed for some time, and after a while it's opened again. Immediately after the switch was opened, power P was released on the resistor R. The question: find the heat that will be released in the circuit after opening the switch. So first we close the switch for some time and then open it. And something happens, and after opening the switch, some heat is released in this resistor. The solution is simple. If we denote by E0 the electric current immediately after the switch was open, then the power released in the resistor can be expressed by a standard formula: power equals electric current squared times resistance. And from this formula we immediately obtain the value of this initial electric current. This current flows through the resistor and the inductance coil. As the switch K is open, this circuit is operating and the current flows in this circuit. And the source of current is the coil, which acts as a source of current because of the Faraday law of inductance, of magnetic inductance. The current through the coil cannot change immediately. There is some inertia of the current, and the initial current will slowly diminish down to zero, and during some period of time the current will flow in this circuit. The initial current is the largest, and if we know the initial power, we know the initial current, and if we know the initial current, we know the energy stored in this inductance coil. The energy will then be released into the heat quantity Q, which will be released in the resistance. So the heat quantity, which we must calculate, is expressed using the energy stored in the inductance coil. And as we have already calculated the initial current in equation number 1, we can obtain the final result for the quantity of heat released in the resistor after the key is opened. The second question in this problem is: find the charge that will pass through the resistor after opening the switch. The values of E and R and L are considered known. The resistance of the inductance coil and the internal resistance of the voltage source should be neglected. So, in order to find the charge that goes through the resistance and the coil after the switch is opened, we must use the Faraday inductance law, a law of magnetic inductance, which says that the rate of change of current flowing through the coil times the inductance L equals the voltage on the coil, and this voltage defines the current through the resistor due to Ohm's law. So in this equation we use the Faraday law of magnetic inductance and the Ohm's law. Then we multiply this equation by delta Ti. Delta Ti is a small period of time during which the current does not change considerably. The change in current is negligible, is very small during the time interval t. And after multiplying this equation by time interval delta t, we obtain this equation. And we, after that, sum up all such equations for all the periods of time delta t, from the first period of time up to infinity. When we add all these terms, we must add together all the changes in electric current flowing in this circuit. We know that the maximum current flows in the initial moment of time, and then the current decreases down to zero. So if we sum up all the changes of the electric current during the infinite period of time, we obtain the initial current. So this sum of all currents or changes delta I gives us the initial current I0, which, by the way, we have already calculated. And current times delta T, by definition, is charge delta Q, which flows through the resistance during time delta T. And after summing up all such equations, current times delta T, we obtain the total charge which flows through the resistance. Total charge times the resistance, which comes here from the Ohm's law, from this equation. So with one taken into account, if we take into account this equation, where we find the initial current, we know the initial current E0, and from this equation we can obtain the total charge Q, which flows through the resistance R. So the simple answer is this one, the final answer to this problem. In the end, I want to add that correct solution of each problem is given 10 points. So if we have 5 problems, then the total number of points is 50. That is the maximum score for correct solutions in this academic Olympiad. If a student made some mistakes in a solution of any problem, then he will get less than 10 points for this problem. Such is the way we assess the solutions of problems in this academic Olympiad in physics. Thank you for your attention.